Okay? This theory is particularly useful when the behavior in compression is different from the behavior in tension. Okay, useful when yield strength in tension is different from that in compression. So we've seen in the past that sigma SY yield strength is the same for tension and compression. That's not true for most all materials. Some of them have different yield strength. So if you have a specimen and you load it in tension, it fails at ST. But if you take the same material, load it in compression, it'll fail at a different stress, SC, and ST is not equal to negative SC, negative because it's compression. So if that happens, then probably this is a good theory for predicting failure. Okay, it so happens that SC in magnitude is greater than ST for most materials. So when you draw a plot, actually a Mohr circle for tension, you'll get something like this. ST. For compression, you'll get a bigger circle, minus SC. Then we can draw a line like this. This is the tangent to both the circles. This is the failure envelope. So anything inside will not fail. Hey, see, how are we doing on time? We have 5 minutes. Okay. Okay. Let me just go through this. This is just a derivation which I have already posted on the handouts. I just want to review it. I'm not going to. You're not expected to know how the derivation comes, but I think sometimes it's helpful to know the derivation. This is basically giving you the formula for how to derive an expression for the yield criterion for this theory, and so that you can use it for solving problems. Okay, and this is something which I posted, so I'll go through this quickly. I'm just going through the notes. I'm not going to be writing much, so we'll take this. We'll do this, and we are done. After we're done with this derivation, we are pretty much done. So what I've drawn here are, well, it looks like just so much clutter here, but what I want you to see is I have drawn those two circles I drew earlier. They are, you can see ST and SC. So those two circles, the bigger the circle on the left side and right side are those two circles which I had drawn earlier, just a while back. This circle, the middle one, is some loading condition, some random loading condition. So for any loading condition, you can draw a plane stress element, and hence you can draw a circle. So this is random loading. Okay. Why do I have that? I have that because I'm trying to figure out if that loading condition will lead to failure or not using this theory. Okay. So for a given stress, we ordered the principal stress as sigma 1, sigma 2, sigma 3. This is only for the circle which I've shown with the I guess the markings, the gray markings. So that is only for this one. Okay, it's not for the other ones. Those ones only have SC and ST. So we'll reorder them as sigma 1, sigma 2, sigma 3. The bigger circle has sigma 1, sigma 3 divided by 2, and that's pretty much the circle I've drawn there. That's I've ignored the other two. The two smaller ones associated with sigma 1, sigma 2, sigma 3 have not been drawn. Now, what we can do is we can compute the center of the circles. So the center of this circle is clearly ST divided by 2. The center of this bigger circle is SC divided by 2. Here it is. And then the center of this circle, which is the loading condition, the one which we are considering, is sigma 1 plus sigma 3 divided by 2. Okay, and the radius is clearly st divided by 2, sigma 1 minus sigma 3 divided by 2, and sc divided by 2. Okay, so we have those centers, we have the radius. Okay, now let's move on to, yeah, I'm almost done, just 2 more pages. So then what we do is we'll try to figure out similar circles, similar triangles. This is to set up some equations. So we'll consider this, oh my God, let's see, take this one. So we need to consider OCTBT, this. Then we consider OCB. And then we consider the biggest one, which is OCBC. Okay, now you can take these triangles. You can set up the ratios. So OCC, BC, the sides of the triangle are in simple proportions. That's what I have written down here, and they should be equal to some constant alpha. I write down these equations for OC, OCT, and OCC. Then what I do is I write an expression for, I split this OC as OCT plus CCT. So OC, O to C is sum of this part and this part. That's what I did. And I did the same thing for OCC. O to CC is this part and then this part. So I write that down. I do some simplifications there, which I think will be obvious, and then eventually end up with an expression which if you do some math, this is all math, it's not anything but math. And based on what I wrote down for the centers, you can actually write an expression for that line which I drew, the red line, the failure envelope. This red line is given by, this is the equation for the red line. Okay, it's just telling you if you are given stresses sigma 1 and sigma 3, which is the loading, and if you know ST and SC, then it's basically telling you if this will be on that red line or not. Okay, that's all to it. So this is an expression which looks probably very similar to the MSS equation. The MSS equation was what? It was sigma 1 minus sigma 3 divided by 2 was SY divided by 2, which can be written as sigma 1 divided by SY minus sigma 3 divided by SY equals 1. You just put equal to. So you can look at this expression here and see this expression, and you notice that it's a very similar expression, except that the SY has been replaced with ST, and SY on for sigma 3 is SC. That's because we've assumed that the failure in okay, now let's see how to apply this. When you solve a problem, let's say random loading, you'll get stresses sigma A, sigma B, and sigma C. In the past, we have arranged that in ascending or descending order and use those stresses to come up with criterion for failure. Here we'll do a similar thing. We'll assume that in a random scenario loading condition, we have already computed the principal stresses, and they are sigma A, sigma B, sigma C. In particular, if you have plane stress, for plane stress, the third stress would be 0, right? So that's for plane stress, and we'll look pretty much at plane stress problem here. Okay, so what we'll do here is assume some values for these. So it'll help us to draw the safety region in a sigma A, sigma B plane. Let's assume that the two stresses you get from Mohr circle are positive, and the third stress is clearly 0. That's the plane stress condition. So in this case, the stress 1, sigma 1, will be the bigger of the two values, I should here put here rather sigma A greater than sigma B is greater than 0. So sigma 1 will be sigma 1 will be sigma A, and sigma 3, which is the minimum stress, is in this case sigma C is 0. So this equation will look like this: sigma A divided by ST minus 0 equals 1, which means sigma 1 equals sigma A equals ST. Or they just put sigma equals ST. You could also do the same thing similarly. If sigma B is greater than sigma A is greater than 0, sigma C would be 0, and you can get a similar condition that sigma B should be ST. Okay, next look at this condition where you have sigma A is greater than 0 is greater than sigma B, which means sigma B, well, sigma C is 0, which means sigma B is negative, right? So in this case, we can see that we would write sigma 1 as the greatest stress here, the biggest stress is sigma A, and then sigma 3 is the minimum stress, which in this case is sigma B. So sigma B, and so we can write from this equation now, sigma 1 is sigma A ST minus sigma B is sigma 3 is sigma B SC equals 1. Okay, so we can write sigma A divided by, well, this is the same thing. Let me just write it. Let me just underline this. We'll need it later on. This, we'll call both of them as 1. That just depends on which of them is greater than 0. We could also write, similar to this condition, we could also write sigma B is greater than 0 is greater than sigma A, in which case, and of course, sigma C is 0, in which case we will get an equation which will look like this: sigma B divided by ST minus sigma A divided by SC equals 1. Just reversing the logic, because you could also have that case. So here is 1, here's the second one. Both of these, let's call that number 2. Okay, we are only left with one more case, and that is when both of them, sigma A and sigma B, are negative. So once we have that, we should be ready to make a plot of equations. Okay, so third case, case number 3. 0 is greater than sigma A is greater than sigma B. As always, sigma C is 0. So we can identify the maximum stress. It's simply 0. The minimum stress, sigma 3, it'll be sigma B. And so we have 0 divided by ST minus sigma B divided by SC equals 1. And so we see that the condition is sigma B equals minus SC. Now we could also have this condition: 0 is greater than sigma B is greater than sigma A, in which case we will get sigma A equals minus SC. I won't really write it down, but the same logic. Okay, so with this, we have the third equation. So what I'm going to do is we're going to make a plot of these three conditions on sigma A, sigma B plane. Okay, how do we do that? Well, let's go with equation 1 first. Okay, equation 1 is saying when sigma A and sigma B are greater than 0, and same sigma, both of them are greater than 0, we could either have sigma A is equal to ST or sigma B equals ST. So that would look something like this. So ST, ST. So remember, it's all in this quadrant, right? This is all the positive quadrant. So we have sigma A equals ST or sigma B equals ST. This would be equation 1. Okay, now let's look at equation 2. Equation 2 is these two equations. Here you can see that sigma A is greater than 0, sigma B is less than 0. So if you go back to this, sigma A is greater than 0. So this is positive. Sigma B is less than 0. So it's in this quadrant. Right? In fact, let me just write it as, you know what, let me write it as, these are going to be in different coordinates. Let's say just 2A and 2B. Okay, so we'll differentiate. So this, as we see, is 1, 2, 3, the fourth quadrant. This is the fourth quadrant. Okay, this is an equation of a straight line with a slope given by, essentially it is this divided by this, the negative sign. But the other way to write this down is to identify that this is going to be the x-intercept, because sigma is the x-axis, and this is going to be the y-intercept. So we can do it that way. It's easier that way. So ST is the x-intercept. That's the x-intercept. And minus SC, right? Because the negative minus SC is the y-intercept minus SC. And we need to join these two with a straight line. So this is going to be our 2A. Okay, next we can look at this equation. We see that sigma B is positive, sigma A is negative. Go back here. Sigma B is positive, sigma A is negative, right? Sigma is positive this side. So this is the second quadrant. So this is that equation was in the second quadrant. And we also note that its intercept is ST on the y-axis and S minus SC on the x-axis. So let's go here. So ST on the y-axis, ST on the y-axis, and minus SC on the x-axis. And we need to join that with a straight line, because it's an equation of a straight line. This is 2B. And the final thing left is equation 3. We see this corresponds to both of them. Sigma A, sigma B is less than 0. So that would be the third quadrant, this quadrant. Both of them are negative. And then we also see that the value is SC for sigma A and SC for sigma B with the negative sign. So all I need to do here is draw a straight line. And this is equation 3. So this region is a safe region. Safe region. Also, in general, as a rule, ST is, or SC is greater than ST for ductile materials. Okay, the strength in compression strength is greater than tension strength or strength in tension. Besides, ST is this region is smaller on the first quadrant compared to the third quadrant. So this is a nice way of visualizing, because what you can do now is all you need to do is, once you know ST and SC, all you do is find the sigma A, sigma B, and plot that stress on this plane on this coordinate axis. And as long as that point for that particular random loading is in the yellow region, you could say that the stress is safe. It's not going to break. We could also use this to design, make a design. So when you want to design something, you want to think about factor of safety. So one way of incorporating factor of safety is that so using DCM for design. So in this case, we have N is a factor or design factor, or let's say factor of safety. So sigma 1 divided by ST minus sigma 3 divided by SC equals 1. This is the normal criteria for failure, right? Now, all you do is you say that I'm not going to allow the stress to reach ST. I'm just going to say that the stress is going to be ST divided by N and SC divided by N. Remember that N, the factor of safety, is greater than 1. So the effect of dividing by N makes this stress here less than the actual value, which is ST. So what it's going to be, it's going to give you a buffer as to how much the stress can go before things fail. Now you could simplify this a bit. If you move this N out of this bracket, you get sigma 1 divided by ST minus sigma 3 divided by SC equals 1 divided by N. Is a question. Yes, so the question is this supposed to be uneven, asymmetric? Yes, of course. So this is supposed to be asymmetric because SC is greater than ST in general for a ductile material. And in fact, this theory is for cases when the compressive strength is different from the tensile stress. Okay, so what this physically means, this equation, is that on this particular diagram, introducing the factor of safety would change this contour to look like this. Okay, this is going to be with factor of safety. In fact, this point here will simply be ST divided by N, and this would be minus SC divided by N. So it's all just going to be scaled by a factor of N. So now all you're saying is that if it's to be safe, the design, it should be in the smaller of this, I guess, a hexagon, in the smaller hexagon. As long as your design is within the smaller hexagon, that is, the stress is within the smaller hexagon, it's considered safe. In fact, it gives you a safety margin. This is going to be your safety margin at any point of time. Okay, that is to account for things which you not consider in design. Things which you did not consider in design could be things like a random loading, which was not accounted for. Maybe you designed it for static loads, but the loads are actually dynamic. So that buffer gives you that extra leeway, and so on. Now, this is all these things we've talked about is for pure tension or pure compression. We could also use DCM, ductile Coulomb Mohr, for shear experiments, for pure shear. So a pure shear involves the stress element with only shear strength, shear stress. Okay, now we've seen this with Mohr circle. So this is the face A, this is the face B. If this particular, for this particular loading involving pure shear stress, we can see that the principal stress is actually, well, the stress here at A and B, sigma A and sigma B is 0. So sigma tau, I'm going to draw the Mohr circle essentially. So we have sigma A is sigma B is 0, but the shear strength is tau. Okay, so how do we draw this? Well, A is this face where there's a shear stress in the counterclockwise direction. A counterclockwise direction for the 2D stress element means that the actual shear strength on the x on the Mohr circle is negative. So I would draw it, say here, minus tau. This is for face A. And then for face B, we know that a clockwise shear will be a positive shear. So this will be I think this is confusing. Tau, I'm using two taus. Let me use tau prime here, just where you're not confusing it with the tau, which is the y-axis. So tau prime, and this is the face B. Okay, so all we need is those 2 points. We then draw a circle, that is the Mohr circle. Okay, clearly the principal stress, which is this one, is what? It's tau. And this principal stress, sigma 3 in this case, is minus tau. Why it's sigma 3 is because the minimum stress should be sigma 3. The second stress is going to be 0 because it's a plane stress condition. So sigma 3 is minus tau. So we have tau and minus tau. And so we've pretty much figured out what we needed for this theory, right? We want sigma 1 and sigma 3, which we've got. So now per DCM, sigma 1 divided by ST minus sigma 3 divided by SC equals 1. But we know that this is prime, this is tau prime, this is minus tau prime. So we can write tau prime divided by ST plus tau prime divided by SC equals 1. We can solve for tau prime. It's ST SC divided by ST plus SC. Okay, so if you think that if you write SSY is strength, yield strength in shear, then SSY is ST SC divided by ST plus SC. So why we're doing all this? Well, is we're doing this because we want to identify a criterion for failure in cases where there's pure shear. There is no principal stresses. Well, there is no normal stresses. An example of pure shear would be torsion. Pure torsion would give pure shear, and this formula would be useful in that case.